Alright, so yesterday's vectorization, is that okay with everyone? It was a very simple thing, right? You don't pass example by example because you have GPUs, you can process multiple matrices and multiple examples at the same time. So you keep the whole matrix. Now if I do it batch wise, how will you do it? See, most likely you won't be able to feed all these 60k or whatever k number of examples or whatever million, whatever billion number of examples you have at the same time. So you make batches, right, and run them. So, and that goes well with mini batch gradient descent as well, because one chunk you will be running on. So one chunk you will be running on one GPU, another one on another one, and then you can parallelize this whole training process, right? So, so computer vision right from beginning is very easy to parallelize. Okay. There are other techniques that we will see, things like CNNs, again they are very easy to parallelize. So computer vision from the beginning has been much more efficient in making use of GPUs, but natural language processing was lagging behind. But as we will see, after the introduction of transformer networks, right, in 2017, NLP actually came ahead of vision, because later even everything in vision is being done through transformers. Okay. So today transformers is the de facto network. It does not matter which architecture, which famous architecture you are talking about, it's a transformer network. You can talk about chat GPTs and all those large language models, you can talk about, you know, anything that you talk about, vision, speech, alright. So my question is, I had said this is a neuron, first it computes a linear and then it computes non-linear. What may go wrong if I don't do this, for example? Why do I need? So this is what, if I have 100 layers, all these 100 layers will be, all the neurons in all these 100 layers will be having two functions. One is to compute linear part and then take some non-linearity on it. Why so?
Because not always data are linearly separable. So it will always be a state line separating them. So when the functions are complex, we need non-linearity.
Right. And something more about that. So whatever he said is right. What will happen? So let's say I have x1, x2 all the way until xn. So I have a hidden layer here. So I'll talk about just one layer or maybe two layers for that. So let me start with one. If that one doesn't work, I'll go to two. So I have this one hidden layer. Okay. What will happen if I have no non-linearity here? How do I write equations for this? I mean, it's a fully connected network, everybody is connected to everybody in across next layers. Yes. Give me the equations for this neural network. How will I compute Z1, W1, X plus B1? So we may as well drop B1, or maybe I'll keep it. Yes. So what do I do now? Activation we are saying we don't have. So Z1 is passed, you will have sigmoid here. So what will be the computations here in this case? Z2 is equal to W2 Z1 plus B2. Okay. Now what will be A2? Sigmoid of Z2. Now what goes wrong in this case? And for simplicity, let us say this has n neurons and this has n input. For simplicity, this does not have to be n, but I am keeping it deliberately for the, since we are introducing this for the first time. What will go wrong? See, if you see if I simply write, so let me write Z2. If I write Z2 equal to W2, now instead of Z1 I write W1 X plus B1 plus B2. What do you see here? This is W2 W1 X plus some other multiplications. So this one now I can do, what will be the next term? W2 B1 plus B2, right? What's wrong with this? This is still a linear function of, yes, Z2 is still a linear function of X. So, you know, this thing is still a matrix. So, W2, this thing is still a matrix. So, this whole thing is again just a linear function of X. Have a look at this. Still a linear function of X. If it is still a linear function of X, this is actually Z1 only in some sense. Yes.
सर बट जो linearity है अपने उसको पैरामीटर्स पे डिफाइन करना है लाइक W and D पे डिफाइन होगा ना तो linearity तो कि वो दोनों लीनियर होने चाहिए.
See, these guys are matrices, they are linear. This is a matrix. So, if you want to learn complicated functions of, I mean to, as he said, right, if data is not linearly separable, you need some complicated decision boundary to separate them, right. So, if you have and let us say we are not going to R theta. So, in this case you need a nonlinear boundary, right. So, your final thing that you have here, you can't be just a linear function of X because that function is not capable of separating these points. Whole point is, so what will I do if I take linearity? How will this equation in that case look like? So, let me write this again. I have sigma of Z2, that is my y hat basically, okay. This is my y hat, and how can I keep on, what will be Z2? W2, what will be Z2? W2 A1 plus B2, and what will this be? W2 A1 is some nonlinearity Z1 plus, no, So you have sigma W2 G1 W1 X plus B1. Is this fine? Right? I can't break it down further. Now, what is the role of this G1 here? It introduces non-linearity. Otherwise, what will happen? Otherwise, this whole thing will be just same as this one. And if you have just this one, help me write this as a function of some other parameters. Come back to this. ये बात बताओ, what is right. So what are the dimensions of W1 matrix? What are the dimensions of W1 matrix? N cross N. So W1 is basically N cross N, W2 is 1 cross N. Now, this whole thing becomes what? W1 cross W2, can I multiply these two matrices? W1 into W2 makes sense, right? W2, W1 is there, so it makes sense. What I will get is N cross 1? 1 cross N, 1 cross N. 1 cross N. So there is this matrix times X plus what is W2 B1? W2 B1. So what is W2 guys? W2 is 1 cross N and B1 is N cross 1. So what I will get is a scalar here. So let us say some B1. This B2 is, so how does this whole thing look like? If I call this some other parameter matrix W and if I call this some other parameter B, this is same as Wx plus B, right? That means introducing this layer did not have any effect. This whole thing, we can just remove this one and still get the same equation. Is this fine? Or questions here? So if your neural network hidden layers, right? If they don't have non-linearity, then so it's basically equivalent to removing that layer. Okay. So if you want to have 100 layers, it is better that all 100 of them have non-linearity, else it won't be worth having that particular layer itself. Okay. So we have just reduced a network that was 2-layer network to a single layer network with 0 hidden layers, right? And we could do this because this G1 was not present. If you have this G1 present, you can't do whatever I did before, right? This G1 will stop you from doing that. Now next. So you need non-linearities, this part is done. Now which activation functions do we use? Can you name some of them? So we have seen sigmoid, what else? 10H, ReLU, what else? Softmax. Softmax is something that you usually do at the last layer when you have multi-class classification, okay. And these days sigmoid you use only at the last layer when you have binary classification, and these two are basically the same thing. So softmax will reduce to sigmoid if there are only two classes, okay. So sigmoid, 10H, ReLU, softmax, what else? Sin X, we don't really use them here, okay. We use it in some different sense when, but not as an activation function. I mean, of course you can use, but I don't see people using it much. What else? That's a good one. So what else? Huh? क्या चीज? Yes, yes, that's right. What else? So, which one does ChatGPT like things use? Okay. So, this is U. Okay. Now, I don't remember equation for ReLU, so you will have to tell me. Now, we start with sigmoid. What is sigmoid? What is sigmoid? 1 upon 1 plus e to the minus z. So, you give it z as an input and it is going to give you this nonlinear value. What about 10H? I don't even, 10H is? Plus, no, minus, minus. So, this is 10H, okay, and 10H lies between minus 1 to 1. So, it just amplifies sigmoid a bit. ReLU is interesting because this is what we have seen in, this has been the primary activation function in hidden layers in last 5-10 years now, okay. What is ReLU? So, if you don't really know what to do at hidden layers, just take ReLU. And what is ReLU? अभी इसको करना चाहो ना नीचे आ जाए. हाँ. What is ReLU? So, ReLU is, you know, y equal, I mean, this one. How will you write this function? This is theta equal to 45. So, how will you write ReLU? ReLU of z is max of 0 comma z. And what does this mean? So, for positive values it will be the value itself, but for negative values it will make the, so this is line y equal to x, this is line y equal to x, but you basically bring this here, okay. Now tell me, can you have a function, can you have a non-linear function simpler than this? If I remove that max, so is this an equation of a line, right? So, if let us say I talk about this line, then ReLU of z will be basically z, and this is nothing but line in some sense y equal to x, if I call ReLU, so instead of doing y equal to x, let me just do y equal to z. Okay, so this is just a straight line, this one. Is this a linear function or non-linear function? Linear function. Okay. By the way, did I tell the difference between linear and affine? एकदम शुरू में बोला होगा पहली क्लास में, उसके बाद बोला होगा कि मैं कभी बात नहीं करूंगा इस बारे में. अच्छा AI में बोल दिया था ना, कहीं तो बोल दिया था ना. हाँ ठीक है, हाँ ठीक है. Y equal to z, fine. So this is a linear function. You just make a slight tweak to it and it becomes one of the maximally used non-linearity in your hidden layers, right? Tell me what has happened here. So if you think, this is remarkably simple because ReLU is just, see, there are functions piecewise linear. So this is piecewise linear. If you see, it consists of two pieces, one this one, another this one. Now you can make any function be approximated by a lot of piecewise linear function, right? So you keep on making those linear parts small and small and you can approximate any function. But here in this case we are saying you just have this particular non-linearity is just, I mean, two piecewise linear, let's say. Okay, one piece is this, another piece is this, and it turns out to be so powerful that it's hard to remove this from hidden layers these days. So even when you say, so for example, let's say when GPT uses GELU, GELU is nothing but ReLU only. Okay, so G stands for here Gaussian. So Gaussian, again then linear unit, something like this. Okay, so here what you will see in case of GELU is, and if somebody can give me equation for GELU, that will help. So something like this. This kink that you have at x equal to 0 where this particular function is not differentiable, right? Is this function differentiable at all points? This is differentiable at all points except 0. Okay, so this part, this smoothness of GELU, it is still ReLU, just that this part is smoothened now. What is leaky ReLU? Leaky ReLU is you don't make that 0. Okay, what you rather do is, so this is not line that is horizontal but with a little tilt or slope, right? So then this part is leaky ReLU. I don't know what is the equation of, I mean, there are more than 400 activation functions used by researchers and studied, but ReLU and GELU in hidden layers, right, and they are just roughly same. Softmax we have talked about. Okay. All right, now my question is the following. So what happens, this is my neural network and this is my fully connected neural network. What happens if I initialize my weight matrices with 0 and then start running gradient descent algorithm? Remember, whenever we are supposed to initialize something, we always initialize it to 0. So my claim is, what happens if we have W1 equal to 0 and W2 equal to 0? And it's a simple question to answer. Huh? Why? Hmm. Hmm. But who said weights will not get updated? You initialize them to 0, they will get updated. But we are still right in some sense, so we need to think more about this. What will happen? So you do this and let me know. 1 minute. This is an easy thing. I usually ask this in exams, but yes. Huh? Cost functions will become 0? No, biases are also 0. Why? Why will cost function become 0? Unless you have minima at 0, why will cost function become 0? Or I mean, unless the value of cost function at 0 is 0, why would it become 0 otherwise? So for example, this line is not 0 at 0, right? So just because I have put variable y, it does not mean that it will become 0. So again, your learning will be slow. Abhidhar, learning will be slow in this case, right? It will take a lot of time to do the right thing. What will happen? So if all these things are 0, your output will be so you do the linear pass, what will you get? Let me do it. No, in fact, when I ask this in exams, I will just leave it open. So what will happen? What will happen if W1, W2, B1, B2 are identically 0 to begin with? Okay. Now, what you actually do is you don't initialize them to 0. You initialize them to small random numbers. And again, this paper from Microsoft, if I remember right, this is a very celebrated paper written by Hay et al. So you have to initialize W, all W's, all B's not to 0 but small values. It can be 0.01, 0.1, but keep it less than 1. And generally even above 0.5 will be considered, but it's okay. Anything between 0, 1 or randomly initialized between -1 to 1, that is also okay. Okay, so this part is done. What else can I do in 5 minutes? हाँ.
सर जैसे ऊपर लिखा कि अगर non-linearity नहीं हो तो problem आएगी, अगर linearity ना हो
No, if you don't have non-linearity, then you can basically shrink your neural network. If I have 1000 layers, none of them have non-linearity, you can shrink them to a neural network without hidden layer. They are equivalent.
सर अगर opposite हो कि मेरे पास linearity है non-linear ऐसे तो उसमें
Non-linearity लोगे किसकी भाई अगर है ही नहीं, right? So because you need to accommodate everything, right? So your linear part will accommodate everything, including the weights. So it will collect everyone, make a function. Non-linearity is going to take non-linearity out. Now, why do we do all these things? We do all these things because we don't understand neural networks, right? As I said before, there is something called universal approximation theorem that says one hidden layer is sufficient, but we have absolutely no idea how to make use of that particular theorem. What we know is if we keep on increasing layers, we still know how to handle them. Okay, then that's a good question. So tell me what will happen if I have 1000 layers, for example. What do you expect? So we are classifying MNIST data set and we have 1000 layers in between. They are all doing what they are supposed to do, take linear and then take non-linearity and keep on doing this, okay. What goes wrong in this case? Overfitting. What else? What do you expect? The network will be giving perfect, so network will be trained perfect because there are too many parameters here, too many layers here. I should be able to approximate any function, right? It turns out if you start increasing the number of layers, we can't handle them. So this is your, let's say, number of layers. This is your cost function plotted. It comes something like this and then starts increasing again. So the value of, so there is some sweet spot where the value of j will hit a minima, and as you increase the number of layers, it will start increasing again. So just blindly increasing the number of layers does not help. You add more and things start getting actually worse. And how do you solve it is one of the very fundamental concepts in deep learning, and I don't think I have time to cover that today. We'll start from it in the next class. So I don't know what will I do in the next class by, but these are ResNets. Heard of them, right? So ResNets, basically this paper talks about this fact. So this result is from this paper and it's a very nice paper to read. Even though it is written in the context of CNNs and image classification, it is a super general technique that is used in deep learning or neural networks today. Okay. I think I should stop now. Exactly. So not 100%. So you will have some y, compute j according to that, right? So see, the main thing that is happening there is, if all these guys are 0, right? What will be z2 here? I mean z1 here, z1 1, z1 2. What will be these values? If matrix is identically 0, biases are 0, what will be these values? Irrespective of x1, x2. Okay. So this guy is computing the same thing. This guy is computing the same thing. Now you introduced two neurons here for them to do different things. Now they started doing the same thing, right? At some point later, as you rightly said, when you will start doing back propagation, weights will start having some non-zero values and these two will start computing different things now. So basically you have essentially made learning slower. So it will still do the right thing, but the number of training iterations required is more now. Okay. All right, done for today.